Welcome to the Hodja on Everything. The Space. Chapter 6. Is anybody home? In the previous episode, we discovered that planets come in astonishing variety. Some are rocky, others are giants made mostly of gas. Some are blisteringly hot, others unimaginably cold, and a fortunate few happen to orbit their stars under conditions that seem almost suspiciously comfortable. We also learned that planets do not choose their destinies. Their size, chemistry, and future are largely determined by where they form. Today we ask the question that naturally follows. If planets are everywhere, could life be everywhere too? Or to put it rather less scientifically, are we alone? For thousands of years, humanity believed Earth was unique simply because we had never seen another world. That assumption became steadily less convincing as our telescopes improved. We now know that planets are not rare curiosities. They are one of the universe's favorite hobbies. Thousands of exoplanets have already been discovered orbiting distant stars, and the Milky Way alone is thought to contain hundreds of billions more. Once again, the universe has demonstrated a remarkable talent for making humanity feel considerably less special than it had hoped. Of course, finding a planet is not the same as finding a home. If someone tells you they have found a house, your next question is usually not, "Excellent, is it made of bricks?" You want to know whether anyone actually lives there. Astronomers ask much the same question. Discovering another planet is exciting, but discovering one capable of supporting life is considerably more interesting. This brings us back to an idea we briefly met in the previous episode, the habitable zone, often nicknamed the Goldilocks zone. It is the region around a star where temperatures could allow liquid water to exist on a planet's surface, not too hot, not too cold, just right. Apparently, Goldilocks has managed to build an unexpectedly successful career in astrophysics. Notice the careful wording, however. Astronomers say habitable, not inhabited. There is an important difference. A perfectly furnished house is not automatically occupied. It may have electricity, running water, and excellent transport links, yet still stand completely empty. Likewise, a planet can possess all the right conditions for life without containing a single living organism. Estate agents and astronomers, it seems, occasionally suffer from the same misunderstanding. There is another important assumption hiding inside our search. When scientists talk about life elsewhere, they usually mean life as we know it. In practice, that almost always means carbon-based life using liquid water. This is not because carbon is necessarily the only chemistry capable of producing living organisms. It is simply the only successful example available for study. Humanity currently has a sample size of exactly one inhabited planet, which is statistically less impressive than we might like. Even so, carbon turns out to be a remarkably versatile element. It forms stable molecules with extraordinary ease, creating the complex chemistry required for biology. Water, meanwhile, is an excellent solvent, allowing those molecules to meet, react, and organize themselves into something far more interesting than ordinary rocks. Whether life elsewhere follows exactly the same recipe remains unknown. For now, however, it is the only cookbook we possess. The difficulty, of course, is that life rarely announces itself with a large illuminated sign saying, "Aliens live here." We cannot simply point a telescope at a distant planet and expect to see little green people waving politely. Distances are far too great. Instead, astronomers search for something far more subtle, traces that life may have left behind. Imagine arriving outside a house late in the evening. You cannot see anyone through the windows, but the lights are on. There is smoke rising from the chimney. Fresh coffee seems to be brewing inside. You still cannot prove somebody is home, but you would probably feel rather optimistic. Astronomers use exactly the same logic. Rather than looking directly for life, they search for what life might leave behind. These clues are known as biosignatures. One of the most promising places to search is a planet's atmosphere. As a planet passes in front of its parent star, a tiny fraction of the starlight travels through its atmosphere before reaching our telescopes. Different gases absorb different wavelengths of light, allowing astronomers to identify their chemical fingerprints. We are not photographing forests or oceans. We are performing chemistry from hundreds or even thousands of light years away. It is rather like identifying somebody's dinner simply by smelling the air from the other end of the street. Certain gases become especially interesting because, on Earth, they are continually produced by living organisms. Oxygen is one example, although it can also arise through non-biological processes. Methane is another. More recently, scientists have become excited about gases such as dimethyl sulfide, DMS, a molecule produced on Earth mainly by marine microorganisms. Detecting such gases elsewhere does not prove life exists, but it certainly encourages astronomers to look much more carefully. That is exactly why planets such as K218b have attracted so much attention. Observations of its atmosphere have revealed intriguing chemical signatures, including possible biosignatures that deserve further investigation. Notice the language scientists use: possible, candidate, consistent with, requires confirmation. Scientific papers are wonderfully cautious documents. Newspaper headlines, unfortunately, are often less patient. A research paper may conclude, further observations are required. By the following morning, someone somewhere has already announced, aliens confirmed. This is probably a good moment to clarify something. No, this episode is not about UFOs, flying saucers, or mysterious lights performing improbable aerobatics over deserted roads at 3 o'clock in the morning. Those may or may not make entertaining stories, but they are not how modern astronomy searches for extraterrestrial life. Scientists are not waiting for spacecraft to land on the White House lawn. They are patiently analyzing light, chemistry, and statistics, looking for tiny clues hidden inside the atmospheres of worlds we may never visit. Sometimes the most exciting discoveries arrive not with dramatic music, but with a graph, a spectrum, and a great deal of cautious optimism. For all the progress we have made, one remarkable fact remains. We have discovered thousands of planets. We have identified worlds that may be habitable. We have learned how to read the chemistry of distant atmospheres. Yet we have not found convincing evidence that life exists anywhere beyond Earth. That silence brings us to one of the most famous questions in modern science. In 1950, the physicist Enrico Fermi was having lunch with colleagues when he asked a question so simple that it has puzzled astronomers ever since. If the universe is so unimaginably vast, if planets are so abundant, and if life has had billions of years to emerge and evolve, where is everybody? Today we call this the Fermi paradox. It is not really a paradox in the mathematical sense. It is a mismatch between expectation and observation. The numbers suggest that intelligent civilizations ought to be common. The sky, meanwhile, remains remarkably quiet. There are many possible explanations. Perhaps intelligent life is genuinely rare. Perhaps simple life is common, but complex life almost never evolves. Perhaps technological civilizations usually destroy themselves before learning how to explore the stars. Some scientists call this possibility the Great Filter. It is not exactly the sort of phrase one hopes humanity has already passed. Or perhaps the explanation is much less dramatic. Civilizations may be separated by extraordinary distances. Radio signals weaken. Stars drift through the galaxy. Entire species may rise and disappear before another civilization even notices they were there. The universe is old, but it is also unimaginably large. Sometimes silence is simply the sound of distance. There is another possibility that I rather enjoy. Perhaps everyone is listening. Nobody is talking. Imagine entering a room full of strangers. Everyone waits politely for somebody else to speak first. The universe may occasionally resemble the world's largest awkward dinner party. Whatever the answer, the remarkable thing is not that we have failed to discover aliens. The remarkable thing is that we have reached a point in history where the question can be investigated scientifically. For the first time, humanity possesses telescopes capable of analyzing the atmospheres of distant worlds, detecting molecules that may hint at biology, and searching the galaxy with something better than wishful thinking. We may not have found our neighbors yet, but we have finally learned how to read the doorbells. In the next episode, we will assume, just for a moment, that someone eventually does answer. If intelligent civilizations exist, how advanced might they become? Could an entire civilization harness all the energy of its parent star? Could a civilization build colossal structures around suns, or even spread across an entire galaxy? To explore those possibilities, we will discover one of the most fascinating thought experiments in astronomy, the Kardashev scale. It turns out that measuring intelligence may be less about IQ and far more about electricity. This concludes Chapter 6 of The Space. Is anybody home? Thanks for listening. See you in the next episode.